do this. I can just throw them out.
Do we need to understand all of these, like the recursion theorem as well, to do this question?
Where's the question?
Because there's a lot of stuff we.
Well, we definitely need to understand the first definitions, right? Because this thing sub E is important. Okay. Yeah. Prove by considering equals plus 1. Infer from this construction that K is not computable. So let's just skip talking about the question. Where is K?
Right above the box, the question box.
K equals this. We don't have down arrow yet, so we probably need it. Hey, undecidability of the halting problem. Guess you get to see the proof of it. There we go. Yeah. Wait, is this the proof? Yes. Good. That's not so bad. Okay, so you're gonna have to know these arrows. So the answer is yes. We should read at least. Oh, maybe not the cleany thing. I haven't. Does he use the cleany stuff in theorem 24.8 though? That's the real question. Doesn't look like it off the top of my head. The following technical lemma is necessary for the proof of the recursion theorem, which follows. But okay. Vehicle for transfer blah. Well, let's start by going over it. Look, we at least need these definitions. So let's start by going over that. Then let's skip to the Turing machine stuff. Then to the halting problem stuff and see if we can get away with just that. And then if we can't, we'll go back to the recursion theorem. We'll recurse and go back to the recursion theorem. So, are milkshakes available anywhere? Reasonably close?
Yesterday.
Where were the milkshakes?
And the milkshakes.
Oh yeah. How about that? I've never actually gone to that.
Is yesterday reasonably close to today? Like that's the question.
Oh wait, when is it? Tuesday?
Every Wednesday.
Wednesday? I'm still striking. I can't get a milkshake next week. Okay. So what was it? I didn't know picketing would come at such a high cost.
I can get you one and bring it to you.
I don't know if I can endorse. I don't know if I could endorse the crossing of the tickets by drinking the milkshake. Though. That's a more unethical question. I'll have to put to the GSU higher ups. Okay, so definition 24.1 though is a mouthful. It's actually not that. Are you hiding from it? But it's not that complicated in some sense. What it's really doing is, that's a unary partial computable function, right? But what this mu thing, is that what this is? No, psi. It's psi.
I think it's 5.
That one's 5. That one's 5.
Try it on this side.
What's this one then? No. What's that?
I think that one is 5.
Okay. And this is psi?
Yeah.
Okay, fine. So we're trying. So enumeration. Are people familiar with that term and what's it used for? Okay. So to enumerate is basically to make a list. It's basically to make a list of everything. So notice that the n, nothing happens to the n. The n is just the input to our function. What is the e doing? So this function is, you've got a binary function equal to a unary function, right? But what do we think the e is doing? If we're trying to enumerate all of the unary unary partial computable functions, if I make a list, what is something I often include in my list to make it better organized?
An index.
An index.
Right. So is there one e for every partial? Okay.
Because there exists a natural number e.
Where does the exist come in the order?
The exists comes in that it says that everything is in your list. So that's what it's saying, right? Because it's saying for every unary partial computable function, you can find a natural number e that is the index of it.
Right. It's not that there's a single e for everyone. It's that everyone has its own e.
Yes.
Right.
That's what all these very long words are trying to say, is that it's defining this binary computable partial, a computable enumeration of the computable partial functions. All it's saying is that you've got a binary function. one of these all would be is a binary function that takes as input a natural number and an input and outputs the output of some unary function that matches that index on F. So basically, it can compute any unary partial computable function with the correct E. Does that make sense? That's all it's doing. It's just an index. Not that scary. I don't even know if we really want to talk about 24.2. I mean, a computable enumeration of the partial computable functions is acceptable. So we say it's acceptable if there exists a total computable function f. So that we can such that for all E, what is the subscript E? So this is this. So notice for definition 24.2, it's a little bit confusing because we're now using psi as what we were kind of using phi for before, right? That's all this subscript E could mean. And in fact, he redefines psi in this second definition. So this is a bit like of a tricky definition, mostly because he's reusing notation for different stuff. So let's see, such that for all E, you've got a computable enumeration of the partial acceptable for total computable function F. It's useful to think of F as a compiler. Okay, so yeah, it's just changing, because notice that
So the phis are the same in both, right? Both, in each case, phi is the
yes.
gross thing.
Mm-hmm. I see. So they're both they're different indexes. And what it's saying is there exists a total computable function that maps between them. So essentially, if I give you the index for some function in size indexing method, in size list, you can think of it almost as, then there exists a function f that is total and computable. So any input to it will halt in some finite number of steps. And what it halts on is the index by a different indexing method for that same function. Does that make sense? I feel like somebody has a question, but maybe I'm wrong. Put a picture up.
Wait, so why does psi have an index now when it didn't before?
Because you redefined psi. Notice psi is now a computable enumeration of partial computable functions, which I assume is just this, but with computable and partial functions.
So I think psi in the second one is the same kind of thing as phi in the
Keep
first one.
moving
Like
this
we
around
defined this thing phi,
People can't
and
hear
that's just
otherwise.
what psi is one of those.
Middle of it is probably fine. This room is improperly wired, so it's all a bit of a mess. Because there's like a little grate under here that is supposed to be in the middle of the table, but the wires come out of the floor, but they don't. So anyway, yeah, let me draw an example.
Did you go to class?
Yeah. And did this make any sense in class?
I don't think Stuart watches the videos, fortunately. So the comment hopefully will not offend him.
You know, like makes sense as you're hearing it. You're like, oh, you
I know what you mean.
This goes from this step to this step, but then
Most lectures do not leave sufficient time for someone to
Like
attempt to
processing
utilize them.
processing.
Yeah, you're processing it, and then when you attempt to utilize it, you realize the flaws in your processing of it, and then you're like, oh, well, I wish I'd figured this out in class so I could ask. So you can think of it like this. Natural numbers, let's say, start at 0, so it's only infinite in this direction. But let's say I've got some function. I'm going to call them something, g's. Let's say these are like unary partial computable functions. And this is the whole list of them. You know what? I'm going to give them completely. Their numbering is entirely arbitrary. So I think I'm just going to give them random numbers. 2, 17, 5, whatever. Stuff like that. Let's say this is our psi. By definition, is this lecture 24? By 24.2, notice though, because member size different in part 1. So this is some ordering. So by psi, psi is going to have some e, and this is e equals 1. This is e equals 2. E equals 3.
Are those baby g's?
They're all unary partial
so they're
computing
what
functions.
psi was in the first definition.
Yes.
Yeah.
Yes, exactly. I wish we had not overloaded notation, but such is life. Okay, the point of the second definition is that if I take another enumeration that, okay, well, first thing I'm going to point out is that, let's just think about this first. This is probably going to be entirely different. Okay, so let's call this E prime. So I don't overuse notation. Okay, these lists obviously do not match up, right? The point is, F, they're, what's it called? What is we're talking about acceptable or something? Is the wording yeah. So this is acceptable if for all other enumerations. So oh, this is probably off. Nope, it's on. This is a bit of an abuse of the exist notation. But no, sorry, it's for all. Okay, I just want to make sure we have our quantifier straight. I'm going to put a comma here so it's more clear these are separate. We want to say for all psi, there exists an F that does the following. It takes in your E value. This is total and computable. So any E is a valid input. Right. But equals, let's say like, so if we get 1, we might get like, they haven't changed where they are, but we have pointers. So let's say, actually, I'm going to make this example a little easier now for myself. Let's say 5, G2, G17. So let's say these do appear just in the wrong places, because this makes it easier to think about. Good. So now, when we get a 1 as an input, F of 1 is going to map to here. F of 2 is going to map to, wait, F of 2 is 17. Sorry, it's going to map over here. Equals 5, and F of 3 equals 3. So the point is that this can take the indexes from this and point you to where they are in this, and that this is acceptable if that's true for all other enumerations, essentially. Computable enumerations. Does that make sense?
I have two further questions.
Sure.
One is f of bijection.
Yeah.
So then two, does that mean if that there exists one acceptable phi, then all are acceptable? Because you can just like, so that phi, you have a map in this thing to this thing, and then you just move it around, you can compose them and get from anywhere to anywhere.
Presumably. I haven't seen this concept before, but that makes sense based on the little I now know about it. Yeah. Seems like it would create like a network of all of them being acceptable, right? Yeah. I agree with that reasoning. I don't immediately see a problem with it. But yeah, does this make sense now then? Cool. This hopefully also helps with 24.1 a bit of just like understanding it's just like an indexing of, yeah. Cool.
Where's
Oh, that completely makes sense now.
Have to put them off sides. Cool.
Oh, so that's 24.2. What you create with the FV.
Yes.
Okay, that makes sense.
24.1 is just this. Right?
Well, that
it's-
one and the other one, right? And the side.
Well, well, by the language of 24.1, psi is what I'm calling G right now. Psi is different in 24.1, so I just kind of want to forget about it while we're talking about 24.1. Let's let these be our unary partial computable functions, and that all unary partial computable functions are captured in this database somewhere.
Decided I really need a sandwich, so I'm gonna go get one.
Cool. Feel free to come back. We'll probably be here for a little while.
I will. I'll also be contacting you, Scoop. Thank you, guys.
Let's see. No problem. So let's see. Okay. Well, that.
So I'm just one thing I'm confused about is how you're labeling these.
Mm-hmm.
So
Labeling what?
well, isn't jeez, I don't know. Is that phi? And then that one's psi.
This one's phi. This one's psi.
Yeah. So phi is binary, right?
Phi doesn't matter what phi is in the second in 24.2. Yeah, they're both
Oh,
different.
are you kidding me?
Yeah,
They use
yeah.
different names.
I'm right.
Like,
That's
I didn't write the
confusing.
lecture notes.
Okay, fine. All right, that makes
Right.
sense. I'm mad. Okay. Cool.
So yeah, so this was forced. This isn't that different from 24.1. It's just forced to be binary in 24.1, and it's not forced to be binary in 24.2.
Okay.
Does that make sense?
Yeah. Cool. So for the theorem, we want to tell if this will halt.
Yep. I'm gonna stop this and just label.